Hi everyone, how you guys doing? Just let me know quickly if my volume is fine, if the audio is clear so that we can get started. Alright, Sai. So let's get started. And let me welcome you guys to Unacademy JEE English. This is a brand new channel by Unacademy, India's largest online learning platform for IIT JEE. And here everything is taught to you completely in English so that no student feels left behind. So this series, as I keep reminding you guys, is aimed for 2020 aspirants. So the scope of these videos is about quick revision of key concepts and problem solving. Focus more on problem solving. All right. So this is lecture 2 of momentum and center of mass. All right. So before we move forward, let me introduce myself one more time. All right. So my name is Rohit Dixit. I study mechanical engineering from IIT Delhi, and I have 7+ years of teaching experience, wherein I have taught at the biggest of the names in the coaching industry. All right, and I myself was JEE rank 447, and I've coached many students to top ranks like those, and I hope I can continue doing that with you guys here. All right. So moving forward, let me also tell you a bit about the Unacademy subscription and its benefits. With your Unacademy subscription, you get live classes, you get to interact with your educators, you have live polls and leaderboards, you have test series and analysis, and you have live doubt clearing sessions. All right. So trust me, these plus points are a huge boost when it comes to your JEE prep. All right. Hi Sandeep, how are you? Namaste. Hope you're doing well. Now, on top of all these benefits, you obviously also get access to India's best educators with your Unacademy subscriptions. Don't forget this. All right. Next, how do you get this subscription? It's very easy to get this amazing subscription. Follow these easy steps. Install the Unacademy app. And once you've done that, go to your plus section, select IIT JEE as your goal, and click on that Get Subscription button. All right. And when you're getting your subscriptions, if you notice that the pricing is very reasonable, it's very fair. For a 24-month subscription, the pricing comes to roughly about 1,500 a month, which is 50 rupees a day. So Unacademy is providing you quality education at very affordable prices. All right, so make use of that. And on top of already affordable prices, if you use my code RD Live to get your Unacademy subscriptions, you get additional 10% off. So don't forget to use my code RD Live to get your subscriptions, and you will get an additional 10% off. All right. Also, you can join us on the Telegram app using the link shown there. All right. So join us on this channel, and you'll get all the updates of all the sessions and lecture schedules happening on JEE English. So now, without any delay, let's get started with today's topic. Hello, Norma. 60 teachers at plus, and there are thousands of students. So teacher not able to answer doubts. Okay. So Noman, for that you have your own doubt clearing sessions, right? See, I don't know about others, but I will try to definitely keep it interactive because unless a discussion is interactive, the learning of students would be incomplete. All right. So I will definitely try to keep my sessions as interactive as possible. All right, Noman. I hope that answers your query. Okay, so why don't we get started with today's topic, which is momentum. But many students in doubt class also as on plus. Okay, no worries. So I can always offer you an extra doubt session, maybe a one-on-one doubt session also, if you think your doubts are not getting resolved in your doubt classes. So don't worry, you can reach out to me and I'll try to help you as much as possible. Great. So let's get started. All right. So as I told you guys yesterday that we studied what momentum is and what is the need of momentum, we realized that F equals ma equation is only valid for a point mass. So what happens when you need to analyze a system of particles? Then what you saw was that the Newton's second law for system of particles can be written as summation F external, summation of F external would be equal to d of p system by dt, we realize that this expression or this form of Newton's second law can also be used for point particles or system of particles, all right, or on any extended object, all right. So that is the entire idea why we want to know more about momentum, because the momentum approach is more fundamental. F equals ma equation is just a specific case for a point mass, okay. This is a more fundamental approach. So we also realize that as a special case, if you look at this equation, what happens if I take f external as 0? So what happens if summation f external is 0? So you will realize that in such a case dp system by dt would be 0, which would essentially mean that the momentum of your system remains constant. Alright, it's a constant, that is why when you differentiate it, you're getting 0. Noman, I think it would be a better idea if you can give your contact number here. I'll try and call you, okay? I don't want to give out my number on a public platform like this. Right, because it's not only you guys who might be seeing this, I don't know. I mean, so you can do one thing, you can give me your number here. Yeah, if you really want, you can either give your number here or you can give your number on the Unacademy platform. Go to the help. Okay. So I will try and get to you. Okay. So I'm noting down your number. Just give me a sec. Alright, so I've got your number. I'll give you a call as soon as possible. Okay. So anyways, in any case, so any one of you, if you want to get in touch with me, so what you can do is either leave your number in the chat or you can go to help on the Unacademy platform and leave your number there and just inform them that you want to get in touch with me. They will contact me with that information. All right. So don't worry. It won't be a problem for you to get in direct touch with me. Hi, Bhavan. How are you doing? No problem, no man, no problem. All right. So once we realize that, and I also spoke about the fact that what happens if I take the entire universe as my system? You know, if I consider every object in the universe as one system, then obviously all the forces become internal, all right? And since there is no external force, the total momentum of my universe remains constant. And I also told you that the conservation of momentum turns out is a very, very, very fundamental principle of physics, all right? So though we derived this conservation of momentum with the help of Newton's third laws, turns out that even in cases where Newton's third law fails, the conservation of momentum still holds. That law never ever gets violated. So there are some fundamental laws of physics which we believe are the laws of nature and they never get violated. We have never seen any violation of them. For instance, even in quantum mechanics, the conservation of momentum will hold. Your Newton's laws won't be applicable. Okay, I'll do that. Uh, okay, sure, I'll do that. I will try and do that. I'll create my own Telegram page. Okay. Yeah, I guess it would be better. All right. So that is what I was telling you. So turns out the conservation of momentum principle is so much more fundamental that it is applicable anywhere and everywhere, even in relativistic mechanics, quantum mechanics. You know where your Newton's laws fail, conservation of momentum always holds. Okay. So anyways, we had this problem. Yes, I had given it yesterday, and Pawan says the answer is 130 newtons. Let's see. This is an easy one, straightforward. So the ball, tennis ball leaves a racket with a speed of 65 meters per second. The mass of the ball is 0.06 and the time of contact is this. Okay, so you know what the impulse would be. So you know from impulse is nothing but change in momentum. Alright, I'm only talking about the magnitudes here. Vector signs are not being considered because I already know the directions of impulse and force would be the same. So when I realize what my impulse would be, that will be 65 times 0.06. Alright, and the time. So this is my delta P and delta T I already know has been given to me as 0.03 seconds, and I know average force F average is nothing but delta P over delta T. So yes, Pawan did get the right answer. The answer would be 130 Newton. Alright, so let's try one more problem. So in this problem, I've told you that a 12,500 kg wagon is moving on a frictionless rail, essentially, with a speed of 18 meter per second. If an additional mass of 4,500 kg is dropped into it, what will be the new speed? So you have a wagon, a rail car, alright, so the weight of that has been given, and it is moving on frictionless rails, alright, and suddenly I drop another mass into it. So its initial velocity was 18 meter per second. I dropped another mass of 4,500 into it. You to find the new velocity. Alright, so how do you do that? Yes, dp by dt is force moment. Good evening, Kushal. Oh, by the way, guys, let me tell you, do not forget to join me today at 5:30. I'm going to show you some demonstrations that will make you see physics. Alright, I'll try and make physics come alive. Alright, so I recorded some demonstrations yesterday in the night, in dark, using some lights and some things. And do join me when I show you those demonstrations. Trust me, I mean, they'll actually show you that what we talk here in theory, it is actually what happens, alright, in practice. So though those things are not very intuitive, but I will actually show you things happening. So trust me, it will be very interesting. So do join me at 5:30. And now because of that, I may have to cut this session short. I think I'll finish this session at 5:15 so that I have some time to prepare for the next session. Alright, and still just remember to join me at 5:30 for some special demonstrations, probably something which you've never seen before. Okay, it's going to be really interesting. Alright, so let's see what this problem is. So here we've been told that the initial weight has been told and the 18 meter per second initial speed has been told and additional mass has been dropped and we've been asked what is the final speed. So how do you go about this? You know, when this is dropped, there is no external force acting on this, right? Why? In the x direction. In the y direction there is. So since momentum is a vector quantity, remember, if in one direction there is no external force, the momentum of that direction will be conserved. So you realize I can write summation, if summation fx is 0, then px will be constant. Alright, similarly if summation fi is 0, then py will be constant. So because these are vector quantities, I can look at their analysis from component by component also. Alright, so in this case, there is no external force in the x direction. So I can say that their x momentum would remain the same. Alright. So obviously, what was the initial x momentum? The initial x momentum was p initial x. I'm only talking about the x momentum because I know x momentum will remain conserved. It was 12.5 into 10 to the power 3 into 18. And let us assume finally the system starts moving with a speed v. So I know what is p final x. P final x would be, this would be 1.7 or at 12.5 plus 4.5. Yes, that would be 7, 1.7 into 10 to the power 4 into v. Now all I need to do is equate these two. Alright, and I will realize that my v would be 12.5 over 17 times 18. Yes, so roughly 2 by 3, I can roughly approximate to 2 by 3, slightly more than 2 by 3 it's going to be. So roughly 70% of what I've been given, so 70% of 18. So that would be around 98, okay, that would be around, around 132. Yeah, that may be correct. So I'm trusting Pawan's calculations and I'm writing the answer as 13.2 meter per second. Alright, so again, a very simple one. All you need to do is look and find out whether there is an external force acting in one particular direction or not. If there is no net external force acting in any direction, then the momentum of that direction will remain conserved. Alright. Next, let's see about this problem. So, you've been told a billiard ball of mass 200 gram is thrown against a fixed steel plate it rebounds as shown. Alright, you'd find the change in momentum of the body. Now also explain what happened to the conservation of momentum. So there was a fixed plate. Alright, so let's say this plate was fixed into the ground, maybe, I don't know. Let's assume this was fixed into the ground. Alright, now this ball strikes it with a speed of 20 meter per second, and it rebounds with a speed of 18 meter per second. Alright, you have to find the change in momentum of the body, or the impulse that the body felt, and also explain what happens to momentum conservation here. What is happening to momentum conservation? Yes, the body is not perfectly elastic, that is why it is coming back with that speed. That is fine. So the impulse is very easy to find. The impulse would be 20 plus 18 into 0.2, right? So it will be 38 times 0.2, which is 7.4. Alright, the change in momentum is easy to see. You can see this straightforward. Alright, delta P would be 18 minus 20 times 0.2. Always remember to take your units in SI, alright? That is one common mistake that you make. So don't forget that. Always convert your units into SI. So that will be 38 into 0.2, which essentially would be 7.4, 7.6 rather. Alright, kg meter per second. Alright, this is easy to calculate. Now the problem is, see, if I consider my steel plate and the ball as one system, let's assume that they are one system. Alright. Now what is happening is, yes, Pawan. So initially the system had a momentum in this direction, right? P initial was in this direction. P final is in this direction. Alright. So why is the momentum changing? Why is the momentum changing? That is what I'm asking. What happened to conservation of momentum? Why is the momentum of the system different initially and different finally? So can you think of a reason? So there is a very simple explanation for that. First of all, let me tell you. First of all, there is a very simple explanation. The simple explanation is that you can say that this was fixed to Earth. Right, so Earth must have provided some force in the x direction. So you realize in what direction is the change of momentum. The change of momentum of our system happens in the direction of plus x axis, which means the Earth must have applied a force in the direction of plus x. You know, this must be the force by Earth on plate, so that the system changes momentum. Alright. Okay, I'll try to be louder maybe. Is it any better now? Now just remember, what happens if I tell you, what happens if I take all three as my system? What happens if I define my system as steel plate plus Earth plus that ball? So now, of course, you can say that there is no external force. Alright, I'll try to be louder, don't worry. Alright, if I take all three of them in a system, then you realize there is no external force. Now why is the momentum changing? Alright, I know that even before the collision and after the collision, you know, the steel plate and the Earth did not move. Alright. It's only the ball which changed its direction. Alright. So what happened to conservation of momentum? Why did the total momentum change? Low-end gamer, that is the advantage of studying online. You realize there are all the videos of the topics which have been covered so far. So take out some extra time. Of course, you'll have to take out extra time. You'll have to put in some extra effort and go through the videos of the topics which I've already covered. And that is the only way. You have to put in extra time. You have to put in some extra effort. All right. and watch these videos, then practice some problems on your own. Watch the next video, then practice some more problems on that topic. And that's the only way. You just have to put in that hard work, put in those hours. All right. So, as I was saying, how do I explain the change in momentum if I take all three as my system? So, any ideas? Let me know, guys. Let me know quickly. What is happening? Where is the momentum going? Why is it changing if I take all three as one system? If I take the steel plate, the earth, and the ball as one system, I will still see that my initial momentum is different from the final momentum because earth and plate are stationary, right? I don't see my earth and the plate moving. So what is happening? All right, no tries also. Come on, think about this. Sir is moving, sir. I'm not sure what you mean by that. Hello, Vineet, how are you? So, you'll have to elaborate a bit, Pavan. Elaborate a little bit more so that I can understand you clearly. I'm not sure I followed what you were trying to say. Yes, essentially that is it. We consider the velocity of Earth to be zero, but even if I do that, the mass is roughly infinite compared to the mass of the ball. So that is why infinity into zero could have been a significant number. Alright. You know in your maths this is not defined. Infinite into zero is undefined or indeterminate. But it can have a finite value. Right? This operation can lead to a finite value. That is what. So yes, Pavan is absolutely correct in saying the Earth actually would have moved with some velocity, but practically that velocity is negligible due to the very large mass of Earth. And if we take into account that negligible velocity, then yes, momentum conservation is holding. Okay, it does not get violated ever. Don't worry about it. Even if you don't see it happening right away, it is because one mass is very massive. So that is why you're ignoring its velocity. All right, now let's take you to a tricky problem. All right, so this is a tough problem. So this is something which could be asked in JEE Advanced. So all right, the earlier problems are usually very simpler, much simpler. So they would be more relevant for your JEE Mains. Let's talk about one problem which may be of advanced level. All right. So you've been told that there is a situation wherein two masses of m and capital M and small m are kept like this. All right. So there's a pulley. So the pulley is fixed to some ceiling. All right. And you have one mass capital M which is lying on the ground. All right. So this is resting on the ground. And you've been told that you can realize here the string is slack. So the string could have come to this height, but I am holding small m slightly above this level. If I left it, if I leave it, it can come down to this level. But I am holding small m above this level so that the string becomes slack. Alright. So now what I do is, right, so consider this was sitting on the ground. After the pulley, this could have come up to here, but I raised it by some distance. Alright, I raised it by some distance so that the string became slack here, and then I released it. So you've been told that after falling from rest through a distance h, a block of mass m begins to raise another block of mass capital M, and capital M is greater than small m. So what will happen is, the moment it falls down from height h, the string must have become tight. Okay, when the string becomes tight, it would apply a jerk on this and a jerk on this. That jerk will give this an impulse. Alright, that impulse would cause it to start moving up. Alright, so that is what the case is. So you've been told, after falling through a distance, a distance h, a block of mass small m begins to raise another block of mass capital M, which is greater than small m. That is connected to it by means of a light inextensible string passing over a fixed smooth pulley as shown. Now answer the following questions based on the given situation. So I hope everybody understands what the situation is. So the situation is that initially capital M was resting on the ground. Small m, if I had left the string to its complete length, it would have reached here somewhere. But what I did was I raised it by a height h and then I released it. So when I release it, when it has fallen through height h, the string will suddenly become tight. It will apply a jerk on both these masses and mass capital M will start to move upwards. Alright. So this is the situation that has been told to you, and so consider this comprehension type of question. You have many parts which you need to answer. So the first part is, what will be the velocity of the mass just after the jerk? Now they have not specified which mass, but that does not matter. You realize both the masses, once the string becomes tight, both the masses will move with the same speed. Why? Because they're connected with the string. So try this. Let's see if you can get this right. No problem, Pavan. You gave the right answer. Alright, so why don't you guys try this problem? Let's see if you can figure out how to solve this one. It's very easy if you understand the approach right. Come on, guys. Let's see. Yes, Vineet, that is the correct answer. D is right. Very well done. D is the right answer. No, Nidhi, I'm sorry, that's not the case. The right answer is D, what Vineet said. Yes, Pavan. Alright, let's see what is happening. So, now this is where I would like to bring to your attention that when the string becomes tight, uh, there is a jerk on this, there is a jerk on this. So what happens if I take my system as, I'm defining my system as small m plus capital M plus string. Now what happens? Is there any external force acting on my system? In fact, there is the force of gravity. Don't forget about that. Right? The force of gravity would be acting. Right? Even if this just got raised, fine. You can say that, the normal reaction would cease to act because this just lifted up from the ground. But still, even if this just lifted up from the ground, let's say it was just like this, there is still capital Mg and small mg acting, right? So the force of gravity is acting. However, I still can apply a conservation of momentum. Why? Because the duration of the jerk would be negligible. And m plus mg, the net external force, is a finite force. Alright. So remember this, guys. So there are two conditions under which you can apply conservation of momentum. Either there is no external force. So that is obviously one. Second, if there is a finite force acting, but you're talking about a negligible duration of time. So what is happening is the impulse, would have been force times t. And here, the duration of the jerk is almost negligible. So it's very, very small. So t tends to 0. That is why I can take the impulse of this to be roughly 0. Alright. That is why I can apply. So this will become roughly 0. Why? Because F is finite and T is negligible. On the other hand, if you see, you will say that the momentum of both the blocks will change, right? How's that happening? Because as I said, the duration of the jerk is very, very, very small. And still I realize that on small m, two forces acted, right? Small mg and a jerk of tension, right? Instantaneous tension force. So the point is, this tension force instantaneously would have achieved a very, very huge value. So this would be tending to infinity. So if in this case t is already tending to 0, if in such a case f starts tending to infinity, then impulse will not be 0. Then it will be greater than 0. Alright, so always remember that. So even in negligible durations, if you have a very, very, very large force acting, then yes, it can create a change in momentum in negligible time. And that is the property of normal reaction and tension forces, that they can instantaneously take up huge values. And these forces we call impulsive forces. Remember this. We call these forces impulsive forces, forces which can produce an impulse in negligible time. Mg, however, is a finite, non-impulsive force. So Mg can never produce an impulse in negligible time. That is why when I take this as my system, now the external force is only Mg, and Mg effect can be ignored and I can directly apply conservation of momentum just before the jerk and just after the jerk. However, if I consider only small m as my system, now I cannot apply conservation of momentum for that. Why? Because there are two forces acting on it. Mg, fine, I know I can ignore Mg's effect during my duration of the jerk. However, this tension during that duration will tend to infinity. Trust me, that is what is happening. The tension suddenly picks up a huge value. And just after they gain the same speed, then yes, tension gets reduced to a finite value. But at the time of the jerk, the tension would have taken up a huge, huge value. That is why even in that negligible duration of the jerk, it is able to produce an appreciable impulse. Yes, yes, Pawan. All self-adjusting forces are impulsive. All right, except for one. All self-adjusting forces that can adjust themselves instantaneously. So let me correct you there. Not all self-adjusting forces can adjust their values instantaneously. So one, yes, your force should be self-adjusting. Second, it should be able to do that instantaneously. How about spring force? Spring force can also adjust its value, right? As you compress a spring or as you elongate a spring, the spring force also adjusts its value, right? So isn't spring force also an example of a self-adjusting force? It keeps on changing its value depending on the compression or the elongation. However, spring force is non-impulsive. Why? Because it cannot adjust its value instantaneously. Uh, no, sir, for see, for a spring, if the elongation currently is x, for a spring to instantaneously adjust its value, the x should change instantaneously. Now, for x to change instantaneously, this end would have moved with infinite velocity, which is not possible, right? The end of a spring cannot move with infinite velocity and instantaneously change its elongation. In negligible duration, the change in elongation would be always negligible. That is why, even though the spring force also has self-adjusting properties, right? It can also adjust its values depending on the compression and the elongation. It cannot do so instantaneously, and that is why that is not impulsive. Okay, good. So as I said, for if I take my system like this, then I can apply momentum conservation. If I apply momentum conservation, then I know what was my initial momentum. Now you will realize also one more thing. Now I am not going to take the vector signs. Why? Because I can just think of this situation like this, that they are moving like this. Alright, so they are moving in the same direction. I can assume that this is the case and I can directly apply conservation of momentum. Alright, if I apply conservation of momentum directly along the length of the string, yes, spring force is not impulsive. So if I apply momentum conservation along the length of the string, I can do that also, right? Along the length of the string, though the direction has changed, but I can still apply along the direction of the spring momentum conservation. So what was my initial momentum? Initial momentum was m times root 2gh. The final momentum along the length of the spring would be m plus m times v, and I can equate these two. Reduced mass is something else. Reduced mass is something else. No, this is not reduced mass. So applying momentum conservation, I can directly write V equals m over m plus m times root 2gh. All right. Reduced mass is an approach to solve a two-body problem. All right. Considering one body stationary, in that if both the bodies are moving, then what you do is you analyze the situation. What happens if one of the bodies was stationary? Then the approach that you apply involves reduced mass. This is not that. All right. So that is how you will get your answer. Now comes the another interesting part. You've been asked find the time taken for the body of mass capital M to return to its original position. Alright, so how do you do this now? See what will happen. The moment string becomes tight, we know that capital M was greater than small m. So the moment string becomes tight, the net acceleration would be this guy would accelerate downwards, some a, and this guy would start accelerating upwards. Now, initial velocities were u was like this and u was like this. Right, so this acceleration due to gravity, due to the gravitational force, it'll cause an acceleration of the opposite direction. So these masses will start retarding and eventually they'll come to a stop. So they start from here, come to a stop, and then go back. All right. So you have to find the time in which capital M returns to its original position. So let's try this. I hope you understood what the situation would be like. So that is the first and the foremost thing when attacking any problem. You need to understand the situation. You need to imagine. You need to see what must be happening. And once you can do that, and the solution would not be too difficult. All right. So once the jerk has been applied, once the motion starts, now it's like a normal pulley problem, right? Now it's just that these guys are moving like this. They will have accelerations opposite, so they will retard and then they will move back in the directions of their accelerations, and this m will obviously come back down and fall to the ground again. So you have to find the time in which it reaches back to the ground. Okay. I've given you 4 options also. Let's see if you can get this right. Okay, maybe I don't remember the answer for this one. Alright, the last one also I didn't remember the answer, but yeah, from momentum conservation I could directly see it. So that is why I told you. This one I'll have to calculate. I'll have to use a pen. I can't probably find it without writing anything. Okay, trust me, Vineet. With some practice, it'll be easier. It gets easy. Trust me, I've been a student. I've been where you are right now. So I'm telling you from personal experience. It appears hard, but once you put in enough effort, you understand your concepts well and you practice enough. Trust me, it starts becoming very, very, very easy. And that is the reason I love physics. All right, Savresh, what result? Class 12 result. How have you been? Long time. Okay, which result is that? Well, that's great. I think that's 91%, right? So that's your class 12 result. A 91% score in any exam is very, very good. Congratulations, Sabrish. Well done. So, guys, I hope you are trying this problem. Let's see if you can answer this one. Okay, in the last problem, you remember when I said you can consider this as a horizontal problem. See that why that I said was that you could have imagined that this capital M was like this, the string was slack here, and mass M was moved with some initial velocity u. And when the string becomes tight, the string would apply jerks, and you realize this situation would be entirely same as the previous one. Why? Because if that u was given as root 2 gh, right, then at the time of jerk, you realize the situation would be exactly identical. Why? Because during the duration of the jerk, we are in any case ignoring the force of gravity. So the internal tension would be acting very, very similar here. And that is why the result that you get here would be also true here. See, that is what I meant. So I did not use reduced mass, but I was just telling you because I'm in any case ignoring the result of the force of gravity. The two situations become identical at the time of the jerk then. Yeah, Sabrish, I didn't realize. What? I said congratulations and I don't know what result you're talking about. Is this a class 12 result? And I think I did say that it is very, very good. I mean, 91% for any exam is good. Alright, I hope you guys are trying this next problem. Just write trying in the chat. Sabrash, I did reply to you by the way. Is my voice that low that you couldn't even realize that I responded to you? I hope you guys can hear me. Okay. No responses are coming, so I don't know what is wrong. Let's see. All right, all right. Okay, good then. I was just surprised because I was not getting any responses. Okay, so are you guys trying? Just write trying in the chat. Great, thank you. Just write trying in the chat if you're trying this problem. Okay, all right, Sabrish. Yeah. That is even great. I did not get so many marks in class 11. I remember. I think I got barely, I got somewhere in 80s, probably 88% or something in my class 11th. Yeah, I didn't manage these marks. So you've done well. Trust me, you'll get better marks in class 12 because class 12, you always get better marks somehow than your class 11. I remember I got 88% in my class 11th and I ended up getting 92 in my class 12th. Wow, wow, all you guys are very, very hardworking, I guess. I don't think I was that hardworking in class 11. Very, very well done, guys. So that is very nice, very nice. All right, so anybody, okay, you wrote trying, so yeah, take your time and let me know if you want me to solve this. Okay. Yeah, that is what I've seen. Yes, that is definitely the case. They give you marks very easily. I mean, I remember back when I was there. Yeah, I know. Back when I was studying, I remember anything above 90% used to be a prestigious thing, you know. You'd be proud of ourselves for managing to get 90 plus percentages. And these days, like, there's so many people getting 90 that 90 is almost, yeah, I know, I know. Plus, I think the marking has become very lenient. They give you marks very easily. Hmm. Yeah, I remember I was in ICSC board, so that board was always tough. The syllabus of ICSE board was really, really tough compared to CBSE at least. That is what I remember. All right, so anyone with the answer of this? Okay, that is great. Wow, Pawan. You're one smart guy, man. All you guys are very, very intelligent guys. I'm glad I have such an intelligent audience. It's always easier to teach intelligent students. Yes, trillions, I am in plus, though I have not started any courses as of yet. I'll be starting my courses next month. I have not started any courses there. There are no courses afloat. All right, I will be starting them next month sometime. Okay. All right. So, anybody with the answer of this? Why don't I go ahead and solve this? So, you realize we already figured out what the initial velocity is going to be. So, I already know u and u here. If I can figure out a, then all I have to do is, yeah, I know. Yes, trillions. As I said, I joined. Okay. So two people have given me B answer, so I am guessing that will be correct. So you realize your acceleration was easy to find. Acceleration was net force. Net force would be m minus mg over total mass, which would be m plus m. All right, so that would be your acceleration. And you know when it comes back, I can take it will go up and come back. So time of flight instead of g, I can use a, right? I know my u instead of g. I know I can imagine this block isolated, this capital M isolated, going with a velocity up a, and the value of acceleration due to gravity can be considered a, right? Trillions in plus, we are supposed to have a compulsory doubt session after every 3 lectures. All right, so that is what happens there. So every teacher must conduct a doubt class compulsorily after every three classes. And there I see my plan is that I will be giving you regular class practice sheets. All right. So after every third class, I'll give you a practice sheet. In your doubt class, you can discuss any doubts related to theory or that practice sheet. So all right. So that is how it's going to be. So I know my time of flight is 2u over g, right? 2u over g dash. Assuming my value of g has become g dash, which is equal to a. So I know 2 times what is u. U was m over m plus m times root 2 gh. Alright, and what is my g dash going to be? G dash is going to be m minus m times g times m plus m. So when I solve this, this gets cancelled, and what I'm left with is, okay, that g is not supposed to be here. Yeah, that's what I was thinking. So there is a g here. So when you solve this, you're getting your answer as 2m over m minus m times root 2h over g. That is the answer that I am getting. Let's see. Okay, you guys said B. No, the answer is A. See what you did wrong, guys. You did something wrong. From our book also, yes. Why not? Any doubts are welcome. I mean, there are no doubts that should be left. It's not like I'll only take doubts from my own sheets. No, I'll take doubts from anywhere. Don't worry about it. I don't want you to think that I'm taking doubts from my own sheets because I only know how to solve questions in my own sheets. So you can bring doubts from anywhere, I don't care. Alright, I'll answer them all. Don't worry, trillions. Alright, I hope you guys followed the solution. I don't know if you did though. How did you guys get this wrong? I think the answer for the previous one was small m over m plus m root 2gh, right? So guys, check your... Thank you, trillions. Definitely, don't worry. I will give you the best. Don't worry about it. No problem. Go ahead. Definitely, give it a try. So guys, the answer that I am getting is A. See where you went wrong with your calculations. Alright, so see, this is the kind of shortcuts that I would use as a student. Alright. Once I know my initial velocity, u, and once I know my acceleration, I would just reimagine this as capital M moving under gravity, where the value of gravity has changed to A. And I just have to find out the time of flight. Yes, I will. Okay, so let's see all the shortcuts that I used in solving my problem. See, you need to do that. That comes with a lot of practice. I used to practice a lot and I made shortcuts for everything. That is why you will see I was very fast at my problem solving. I remember when I took my paper, the screening paper was objective. IIT screening, we used to have a screening and then a mains. Mains was subjective. Of course, you can't apply any shortcuts in the subjective paper. But in the objective paper, I used to apply a lot of shortcuts. And with the help of those shortcuts, I was able to finish my paper, I think 12 minutes before the end of time. And I managed an All India rank of 192 in that exam. Alright, so pay attention to what shortcuts I'm using. And maybe you can use them too. So I told you, the moment these guys start moving, you know the initial u, right? This one starts going with some initial u up, this one starts going with some initial u down. So u we have already calculated. What was our u? U was m over m plus m root 2gh. Alright, this was the u that we calculated in the previous part. Now all I need to see is what is the acceleration of the masses going to be. For that I have already told you a trick, that consider this lying on a flat surface. There is your small m, there is your capital M. Imagine this is being pulled in this direction with small mg, this is being pulled in this direction with capital Mg. Now what is the total external force? Take this as one system. Why? Because both the masses will move with the same acceleration. So what is the net force on the system? Net force is capital Mg minus small mg. And what is the total mass of the system? It is mg, m plus m. So the acceleration can also be written in one step. Acceleration would be m minus m times g over m plus m. Right, so once I figured what the u and the a is, now let's look at the motion of mass capital M. What is this mass doing? Let's consider it isolated. So it was kept on the ground. I gave it a speed u, and during its entire motion, what is this guy going to do? So this guy is going to go up and then it will come down, right? And during this entire motion, what is the acceleration? Acceleration is a downwards. Okay, that is the simplest part though. Okay, let me show you from the longer method. Let me show you the longer method. What is the longer method? The longer method was small m, capital M. Let's assume some t, let's assume that this guy is going down with an acceleration a and this guy has an acceleration a upwards. So longer method says for this guy, for mass for capital M, what can I say? I can say that capital Mg minus t equals capital MA, and for small m I can say, so that will be my equation number 1. For small m I can say that T minus small mg equals small ma, that will be equation number 2. You add the two equations, equation 1 plus equation 2, what do you get? You get m minus mg equals m plus m a, or I get my a as m minus m over m plus m times g. So we'll teach which subject in plus? Physics only. Trillions, I'll stick to physics, I think. Alright, so Pawan, this is the simplest part. See, the motion does not matter, right? The initial velocities do not matter. It doesn't matter whether initially they were at rest or moving down already or going up. Yes, trillions, maybe from starting. See, I will be probably launching courses for different topics. Okay. So maybe I'll launch a course which will have, let's say, kinematics, the entire kinematics and vectors for class 11th, and let's say in the entire electrostatics for class 12th. And then the next course that I'll launch probably would be, let's say, Newton's laws of motion, work, power, energy and momentum for class 11th, and maybe magnetism for class 12th. Alright, Pawan. So this is the usual method that you solve with. And obviously the speeds don't matter. The initial speeds do not matter. You only have to consider the forces to find the acceleration. Alright, Pawan. So when you consider the forces, you know the acceleration is going to come the same only. See, this is the same answer that you would have got if you had left them to start from rest. Right, because the forces are same. So the answer will not change because you gave some speed. Even if you gave an upward speed to capital M. So it will still be the same. Now, as I said, once I have figured out the U and the A, now all I know is that this guy will go up and it will come down, and during its journey it will have an acceleration A downwards. So I can think of this as motion under gravity, just that my value of G has changed and it has become A. So I can directly apply that equation instead of having to solve this equation, right? Instead of solving, writing S equals ut plus half at square and then making S 0 and solving that, I know the result. See, my idea is if I have memorized one result, I will maximize it. Because I don't want to memorize too many things. I am already burdening my brain, but since I have already memorized it, let's use the result again and again. So I know this result. I know what the time of flight is. It's 2u over g. Alright, so in this case, the g would be a. Alright, so I can write in this case the answer as 2u over a. Alright, so the moment I do that, what am I getting? 2 into u. U was small m over m plus m times root 2gh. Okay, this seems to be moving a lot. 2gh into 1 over a. 1 over a I already know. It is m minus m times g over m plus m. Alright, so these get cancelled. 1g will get cancelled. This will become root. So you get your answer as t equals 2 small m root 2h over g over m minus m. Alright, that is your answer for time. Okay, I hope you followed this. Yes, Vineet, you said you have a doubt. So, did both you guys follow this? So remember to use such shortcuts. And the more you practice, the more these results would be obvious that you can use this result here also. I mean, again, as I said, I found the acceleration directly in one step. You can also find the acceleration using this, but you realize this is just going to take more time. Alright, so I'm not going to do that because time is crucial for objective exams. If I had more time, I would probably be able to solve them all, right? Most of the times, you guys battle for the time. Even if you think you have enough time for physics, maybe extra time will help you with maths. Maths always takes time, alright? So remember to, do this. Use shortcuts wherever possible. So instead of this entire thing, I'll just write my acceleration in one line as this: net force over net mass. Alright. Then instead of solving S equals ut plus half at square equations, I can directly use this result: T equals 2u over g. Alright, and get my result by directly just substituting those values. That's about it. So you start doing these things, these small little things, and they'll end up saving you a lot of time. So let me know if you guys followed this solution so that we can move ahead. And if you would like me to explain any part, then tell me, I'll explain that part again. Please let me know. Great, great. All right, so now last part is find the fraction of kinetic energy which got lost after the first jerk. All right, this should be easy. You know what the initial kinetic energy was? Initial kinetic energy was half small m root 2 gh. You know the final kinetic energy because you know the final velocities just after the jerk. So all you need to find is find the loss of fraction of k. So this should be easy, by the way, because it's very easy to see the initial and the final kinetic energy just before the jerk and just after the jerk. All right. So solve this and then we can start with the new topic today. Alright, you can solve this later also. I think this should not be too much of a problem. Alright, it should be easy. Just remember, you've been asked to find the fraction of the k lost. So please remember this word lost. So loss would be k initial minus k final, right? So you have to take the loss of k over initial k. So this, how will you find this? Delta k over k initial. So that is what you have to find. Just remember that and you should be fine with this problem. Alright. So next, let's move on. And today we're going to start a new concept, and I wanted to introduce this concept to you guys because I have a demonstration at 5:30 wherein I'll show you some demonstrations related to center of mass. Alright, so what is center of mass? Let's see. So for any system of particles, there is a point which behaves as if the entire mass of the system is concentrated on that point. Alright, so you take any system of masses. It may be a system of discrete masses, it may be a system of continuous masses. So it may be a big object like this, or it may be a collection of many point masses. Hitesh, I think if you use earphones, it'll be better. I've realized that when you're listening to my voice on the phone, yes, it tends to be low, but if you use earphones, it gets better. Trust me, I've seen my own videos also on mobile just to realize how you guys are, if you guys can hear me fine or not. I'm trying to be as loud as possible, trust me. Alright, I'll try to be louder, but use earphones and that should help you. So I'm saying that for any kind of system of particles, whether it is made up of small different masses, or whether it is a huge body made up of very many point masses, there will be, you can find a single point which behaves as if the entire mass is concentrated on that, and all the forces applied on the system are being applied at that point. That is how that mass behaves. That is how that point behaves, in fact. So if you look at this, when this guy is thrown, a randomly shaped bat is thrown, you will see that there will be one point which will follow parabolic trajectory. Now that is what I am going to show you at 5:30. At 5:30, I will actually show you the center of mass of this guy. So I have thrown this duster into air and it will be moving like this. and you will see the center of mass moving in a perfectly parabolic path. So that is the demonstration I've got you today. I mean, I know you see this diagram in the books, but it still doesn't make okay. You can believe it, but you still can't feel it. So today, when you see that demonstration, you'll actually feel it. You will feel that though this is moving like this, the center of mass would be moving in a perfectly parabolic trajectory. You will get to see that at 5:30. So that is why join me at 5:30. I'll be showing that to you. Alright, so the point described above is called the center of mass, alright, of the system. And we can reinstate the principle of conservation of momentum in a useful way by using this concept. So the entire idea is, as I said, why did we introduce momentum? The knowledge of momentum became essential if I wanted to analyze big bodies or collection of particles, a system which has many point masses which can be moving with different speeds. So then I realized I can't use F equals ma equations. I can use momentum, however. Similarly, the center of mass is another way of using momentum and its laws to analyze bigger objects or systems of particles which are made up of many masses. Okay, in statistical language, let's see what the center of mass is. It is the mass weighted average position of the particle, alright, or average position of mass. So you guys know weighted averages. I hope you know weighted averages, what weighted average is, right? So suppose you have 3 rooms, alright. So let's say 10 people here, 20 people here, 30 people here, and let's say the ages. The average age of all these guys is, let's say, 10 years. The age of these guys is, let's say, 15 years. And the age of these guys, all of them are of, let's say, 20 years. Alright, if I told you to find me the average age of the entire sample, how would you do it? You would have done 10 times 10 plus 15 times 20 plus 20 times 30 over 10 plus 20 plus 30, right? I hope you remember this. This is what weighted averages are. This 10 becomes the weight of this value of 10 years. This 20 becomes the weight of this 15 years. Similarly, this 30 is called the weight of this. Why? Because there are 30 people who have age of 20 years. So these are called weights, and this is called weighted average. Alright, so the weighted average will give you the average of all these, right? So that is what you are trying to find out when you are calculating the CM. Turns out CM is nothing but the average position of mass. It is the weighted average of all the masses. Mass weighted average positions, right? Where the weights have been taken as mass and position is what we are trying to find the average of. Alright, so you can see in this also example that essentially what RCM is that whenever these two guys will be moving, there will be a hypothetical point which will move as if the entire mass is kept here, and whatever forces are acting on these guys, that net force, let's say F1 acting on this guy, F2 acting on this guy. So instead of analyzing them separately, you can consider that this point, hypothetical point, has an m1 plus m2 mass, and the entire force of F1 vector plus F2 vector is acting on this. Right. So this hypothetical point moves as if it had all the mass and all the forces were being applied on this. Right. That is what center of mass is. So let's see some more about center of mass, how to calculate it. So if a system of particles comprises of many discrete particles, let's say m1, m2, m3 and so on, and which have position vectors of r1 vector, r2 vector and r3 vector respectively, then position of the center of mass of the body is defined as RCOM equals mr1 plus mr2 plus mr3 over m1 plus m2 plus m3. Right? If you realize, this is what we did here when we were trying to find the weighted average. Right? So this, instead of this 10 years, because here I was finding the average age. So I took this and number of people as my weight. On the other hand, there I am trying to find the average position of mass. So instead of age, I am taking position first. So position into the weight is mass, right? So into mass plus the second position into mass plus the third position into mass over sum of all the masses. That is what I'm trying to do. That is what mathematically RCM is, or position vector of CM is. Alright, so that is how you get. It is nothing but the weighted average, mass weighted average of the positions. Alright, okay, so let's see. If the position, okay, we've already discussed this. Yeah. So if the position is given in component forms, so you can find x, y, z components as xcm would be m1 x1 plus m2 x2 plus m3 x3 upon m1 plus m2 plus m3, which is nothing but I'm just writing my vectors in form of their components. Alright, I can write r1 as x1 I cap plus x2 plus y1 I cap plus z1 k cap and so on. And from there I can see that xcm would be this, ycm would be this, and zcm would be this. Alright. Now, you will notice one very interesting thing. All right, so let me go to this. What happens if I differentiate both the sides twice with respect to time? If I differentiate both the sides twice with respect to time, what do I get here? I'll get d2rcm over dt2 equals 1 over m summation of miai, right? So m times d2 rcm over dt2 equals summation of miai. And I told you before only, what will be the summation of miai? It will be f external. It will be summation f external. I had shown you guys. If I write the f equals ma equations for each and every mass, let's say for m1 I write all the forces acting on it equals m1a1, then for a2 I do the same, for a3 I do the same. When I add, all the internal forces will cancel out on one side of the equation. So one side of the equation is left only with summation f external, and the other side of the equation looks like this. So you realize, what is this? You realize I have gotten that this is equal to this, which means if all the mass of the system was placed at RCM, then this term is telling you acceleration of RCM, A of CM, right? Acceleration of the center of mass. So center of mass is that hypothetical point. Mathematically, it turns out, it appears as if all the mass is kept at this position. Then the rate of change of, double rate of change of this position with respect to time into the total mass is essentially equal to F external. So I'm getting the feeling as if all the mass is kept at the position of CM, and if all the F external is applied to that point, it will accelerate like a point mass. Alright, it moves like a point mass, like all the mass is kept there. That is what we were trying to say when we were defining center of mass. Alright. Okay, so why don't we go ahead and solve one problem? Three particles are placed at the corners of an equilateral triangle of side B as shown in the figure. Find the position of CM of this three particle system. So here is how the particles are placed. I think the side is B, so this would be B. This is an equilateral triangle. This is also B, and this is also B. You will find the position of the CM. Alright, that should be easy. What will be the coordinates of the first mass? 0, 0. Right, what will be the coordinates of the second mass? B, 0. And how about the third? From the properties of equilateral triangles, I know that this will be B by 2, right? So B by 2, comma, what will be the height? It will be B sine 60. So root 3 B by 2. So once you have the position coordinates of all the three masses, you just use your equations of xcm and ycm and you can get the answers. So let's see what the xcm looks like. So I can say for xcm it will be 0 into 3 plus b by 2. Okay. So plus b by 2 into 1 and plus b into 2 over 3 plus 1 plus 2. So what am I getting? I am getting 2b plus b by 2, which is 2.5b, which is 5 by 2b over 6. or 5b by 12. So that is my xcm. Now similarly you can find out the ycm, and that is how you will get the position of the center of mass. Alright, I hope you guys followed this. Tell me if you have a problem with this. It's easy enough. We are just using the definition. We are finding the coordinates of all the three masses. Then we are putting all the values in the expression that we got. Okay. So let me know if you guys are clear about this, because I would like to take a 10-minute break at least before so that I can set up for. Okay, I guess you're telling me yeah, that might be the case. Great. So I'll take a break here. I had planned some more things, but we'll take them up tomorrow, because I think I would like 10 minutes to set up to get the setup ready for the demonstration that I was talking about. So you guys can also use a 10-minute break and join me back at 5:30, please. And we'll carry on this discussion tomorrow. Don't worry. All right. So that'll be it for today. And before I leave you guys, let me also remind you again how to get this subscription. Alright, install the app, go to the plus section, select IIT JEE as your goal, and click on the get subscription button right there. Alright, and do not forget to use my code RDLive to get your subscriptions. Alright, this will make your already very reasonable pricing more and more affordable. So definitely use my code and it will give you 10% off. And if you like today's video, if you think you learned something new, then like this video and share it with all your friends. Also, don't forget to press that bell icon to get notifications of all the future lectures. The slides used in this lecture will be available for download in PDF form by tomorrow. So you can come back tomorrow, check out the description box of the video, and you can download your PDFs. Alright, so don't forget to join us on the Telegram app also using the link shown above. Alright, so join us on the Telegram app to get notifications of all the lectures. And one more time, use my code RDLive to get your Unacademy subscriptions and get an additional 10% off. So I'll see you guys in a bit. Alright, and hope to see you all at 5:30. So I will show you something really nice. You will actually see physics at work. Alright, so don't miss it. Get back at 5:30.